Hello, my name is Georgina Rodriguez. I am presenting the work Learning Styles and Visualization in Numerical Analysis. The other authors are Marta Caligaris and Lorena Laugero. We all belong to the Grupo de Ingeniería y Educación from the Facultad Regional San Nicolás, Universidad Tecnológica Nacional from the Argentina Republic. Traditional teaching of numerical methods is often characterized by overemphasizing algorithmic developments and procedural handlings of the symbolic aspects of mathematical objects. By this way of teaching numerical methods, students construct a partial mathematical knowledge consisting mainly of algorithms, situations that make them manipulate symbols routinely without giving significance to the basic concepts of numerical methods. The lack of articulation between the different semiotic registers that should be acquired does not allow students to make an adequate comprehension of the mathematical concepts involved. Visualization is one of the abilities that is used when conveniently relating numerical methods with technology. One of the meanings of visualization in the dictionary of the Spanish Real Academy is the action of making in mind a visual image of an abstract concept. Visually simulating computer environments can allow students to become immersed in their own knowledge construction. From this point of view, the inclusion of computers programs can be a facilitator of learning processes because they provide means to articulate the different semiotic registers of a concept. Students process information and learn in different ways. They may prefer graphical ways of representing information, printing words, heard information, or the use of experience and practice. These preferences can be classified as VARC, visual, read, oral, and kinesthetic by Fleming and Mills. In different studies, learning preferences of students were determined. For example, in the Czech Republic, the large group of students of educational disciplines consisted of those preferring kinesthetic learning style. Other group studied in a Turkey university concluded that there is no learning style that outranks others for all engineering discipline. Here in San Nicolás, most students enrolled in numerical analysis have shown their preferences for the visual learning style. The viewing habit helps them to establish relationships between different ideas and concepts, developing a greater capacity for abstraction. Visualization is a broad concept. In fact, it is a concept on which there are different conceptions in research on the teaching of mathematics. In the Encyclopedia of Cognitive Science by Nadel, visualization is considered as the ability to store and retrieve representations defining the visual characteristics of environment stimuli, including the graphic symbols used to represent written words. Visualization, for Arkabi, is the ability, the process, and the product of creation, interpretation, use, and reflection about pictures, diagrams, or boards in our minds, on paper or with technological tools in order to represent and communicate information, thinking and developing unknown ideas and anticipating the comprehension. Visualization in mathematics education permits a broader coverage of mathematical topics and allows students access to new ways to approach their own mathematics, as Eliot, Hudson, and O'Reilly says. With visual arguments, students can conceptualize ideas. For Zimmerman and Cunningham, visualization supplies depth and meaning to understanding, serving as a reliable guide to problem solving and inspiring creative discoveries. In this sense, visualization cannot be isolated from the rest of mathematics. In other words, symbolic, visual, and numerical representations must be connected. The use of applications presenting different semiotic registers in the learning process of mathematical concepts lets students interact dynamically with different semiotic representations of the objects studied, promoting conceptual learning. For the teaching of the different issues of numerical methods at Facultad Regional San Nicolás, a set of tools that implement numerical methods was developed using the symbolic software Maple, Silab, and Mathematica. Some of them will be shown here, highlighting their potential. The main purpose of these visual tools is that the user can get a numerical solution for different mathematical problems with the corresponding method in a friendly graphical interface without worrying about the commands needed for this solution. They only have to press buttons. The authors of this paper believe that the use of personalized windows will not only help students to develop the visualization ability, but also enable a dynamic interaction which lets students relate different semiotic representations of the studied object, stimulating the conceptual learning. By this way, students will not only focus attention on the object under study, but also through visualization. They will be able to compare the methods under study, analyze the pros and cons of applying them to discover math concepts, make generalizations, thus developing and promoting a different kind of mathematical thinking. Here, it is the first example. It is a window developed in the software Silab, where the composition methods for linear equation systems can be applied. By pressing this button, you can enter the system to be solved, the matrix and the independent terms. And by pressing the decompose button, you will get the two matrices of the method and also the number of equations operations needed for that decomposition. And by pressing the solution method, you will get the solution of the system. Also, by pressing the other button for Cholesky, you will get the matrix decomposition of Cholesky and the number of operations required. Then, pressing solution, the solution of the system will be obtained, obviously the same as before. Here, students can apply this window to obtain the number of operations of both methods for different size of systems. They will be able to compare the amount of operations needed. Here now we have a second example for solving partial differential equations, a problem that often arises when setting mathematical model of many engineering problems. Most of them generally don't have exact solution and numerical methods are needed so as to obtain approximations. Here it is presented a window for solving the wave equation. By entering the data of the problem, the solution will be obtained. Here the interval, the boundary conditions, and by pressing calculate, a graphical solution is obtained. Also, another window was developed with the Maple 15 software. In this window, the wave equation also is solved by a numerical method, but you can see here the exact and the approximate solution. In the graphical way, students cannot appreciate the difference between these two solutions. So, by pressing the button which says table of values, the values of the solution are obtained so as to compare the exact and the approximate solution, and they also have the error of the two solutions here. What is meant with the use of this window? Well, different semiotic registers are used in this representation of the solutions. A third example here is shown. It is a window developed in Mathematica, a software of Wolfram. Here there can be entered a set of points and the interpolation polynomial of Lagrange and the spline interpolation are obtained. Students here can compare the two interpolations obtained and the difference between them. Well, what can we say about this? Technology made possible visualization in mathematics, particularly in the field of numerical analysis. With some symbolic and numerical software and the widespread of computers, students can acquire mathematical objects in a different way. Students now have tools for developing competencies to argue, analyze, and conjecture, among others. The tools presented here can be particularly important when searching for ways to work with students raised with visual stimulation. However, quantity does not ensure quality, and there are many open questions about which visualizations are most effective in increasing student learning and about how they should be used in the classroom. By interacting and experimenting, students understand better the concept that is being taught. Didactic sequences applied in the teaching must bring together learner and resources to let knowledge arise. It is important to analyze the way that students learn so as to develop sequences consistent with the group for which they are intended. Well, thanks for your attention. You can get in contact with us at this mail. Thanks again.